This is a continuation of section 17.2, and we're going to talk about how to describe a galvanic cell or how to completely describe a cell. Line notation is a shortcut way that we use to describe electrochemical cells. We write anode components on the left, and remember anodes are oxidation. Cathode components go on the right, and remember that um, cathode is where reduction occurs, okay? And then you separate the components by a vertical line. So we have magnesium becoming Mg2 plus. So that half reaction would look like this. And then we have aluminum ions becoming aluminum solid. That half reaction will look like this. So it's just a shortcut way to show what's happening in a cell. So we separate the Mg and the Mg2 plus with a one vertical line, and then both the separate components are separated by a double vertical line, and then we have the reduction component on the right. If you are asked to give a complete description for an electrochemical cell, you have to always include these things. Always include the half reaction and the overall balanced reaction. Include the overall cell potential, which means you have to use that table, add up the numbers, and find the cell potential. You always include the direction of the electron flow to indicate which one is being oxidized and which one is being reduced. And you designate the anode and cathode compartment. So whichever one is losing electrons will be the anode. Whichever one is gaining electrons will be the cathode. And then make sure you indicate the nature of each electrode and the ions present in each compartment. So the ions in the solution should be indicated, and then the type of electrode, like is it a zinc electrode, a copper electrode, a platinum electrode, etc. These are everything you need to include when you are describing a cell, which could take a little bit of time. It's not, it's a long process. So let's give it a try. Okay, so here we are being asked to describe a galvanic cell based on these half reactions under standard conditions. And we are given a standard reduction table, and we're given two half reactions. But notice the both half reactions that we're given are reduction reactions, which is not possible. So one of these has to be oxidized, and I have to figure out which one. So if I look at silver on this chart, the reduction potential is 0.80. If I look at iron on the chart, the reduction potential is 0.77. Now they are very close, but one is still higher than the other. So since silver has a higher reduction potential, it is more likely to be reduced. And since iron is a little bit lower, it's going to be oxidized. So I'm going to flip the reaction of iron. So we keep the silver reaction the same here. And we keep the cell potential the same. And the bottom one, since the iron 2 is being oxidized instead of the iron 3 being reduced, so we have to flip this reaction. So we have to reverse the sign on the 0.77, and so it's negative 0.77. And then we add these two numbers together to get the cell potential, which is 0.03 volts. So now we're going to draw what the rest of the cell would look like, because remember, a complete description is going to also include a picture. So you're going to start with two beakers, okay? On the right side, I'm going to put, well, it doesn't matter which side you start with as long as your electrons are right. So on the left side, I'm going to have a silver electrode, and then in that solution, I'm going to have silver ions. That is according to that half reaction. The concentration of those silver ions is 1 molar since we're using standard conditions. Also remember that your electrode can never be made of ions, so electrodes are solid metals. The ions are what's in the solution. So on the right side, the other half reaction was the Fe2 plus becoming Fe3 plus. Both of those are ions. Both of them go into the solution. So that leaves me, what do I make my electrode out of? Well, I didn't have any solid iron in my equation. So when that happens, you will use a platinum electrode. Okay, so platinum is a pretty neutral electrode. It also can be used as a catalyst. So platinum is the electrode you would use in the case where you have two ions and no solid of that same atom. Okay, so now I have my two components. I need to connect them with a wire. This time I'm going to add a voltmeter in the middle. And you can go ahead and put 0.03 volts on that voltmeter because that's what it would read. And I need to add a salt bridge. Remember, the salt bridge has to be added before the circuit can be complete. And the last thing I need is a direction of electron flow. Since the electrons are coming from the iron to the silver, because silver is being reduced, so it's gaining the electrons, then I will put my electrons here and I just indicate which way they're going with arrows. Okay, so you always want to indicate your direction of electron flow. So we have our two sides, and then we can write the overall chemical reaction as this is our overall chemical reaction because we were transferring only one electron. And then the last thing I need to do is indicate which side is the anode and which side is the cathode. Remember, the anode is where oxidation occurs, and oxidation is loss of electrons. So the anode here is going to be on the left. And then the cathode is where reduction happens, so the cathode is the silver compartment. And those are all of the elements of an of describing an electrochemical cell. I also want to show you something called a porous disk because you could see something like that. So you can see, so far our electrochemical cells have been two separate beakers or two separate solutions, and then we added a salt bridge. But look at this picture here on the left. We have two beakers, or actually it's like this is sort of a device that has a porous disk in the middle. The porous disk is equivalent to your salt bridge, okay? So this is still the same galvanic cell we've been using before. It's just that it's a different type of device being used. And so it could look like this, or it also, you could see a solution that looks like this, and here is your porous disk in the middle here. But the porous disk is equivalent to your salt bridge. It still has ions that transfer to make both sides of the solution neutral.